13.8 billion years ago, everything that would ever exist exploded into being from a point smaller than an atom, or at least that's what we believed. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, wasn't built to destroy our understanding of reality. It was designed to confirm the greatest story ever told about how it all began. Instead, it's uncovering galaxies that formed too quickly, black holes that expanded too fast, and structures that organized far too early. We're about to explore discoveries suggesting that our entire origin story could be completely wrong. If you're ready to question everything you thought you knew about the universe, make sure to like and subscribe, because the truth is stranger than fiction. Prepare yourself. We begin. $10 billion and 30 years of planning produced the most advanced machine ever launched into space. The James Webb Space Telescope wasn't expected to surprise us. It was built to look back through time and confirm what we already believed about the universe's birth. Scientists expected to see small, primitive galaxies taking their first fragile steps of formation. They anticipated finding sparse clusters of young stars barely recognizable as galaxies. Instead, Webb revealed a cosmic nightmare for everything we thought we understood. It's like opening what you think is a baby photo album, only to find portraits of fully grown adults. The telescope showed galaxies that should not exist. These weren't the cosmic infants we expected in the universe's nursery. They were massive, structured, mature systems blazing with the light of billions of stars. Picture this. You're told that a forest takes 100 years to grow, and then you find trees fully mature in just 10. That's exactly what Webb found in space. Galaxies that should have taken billions of years to form were already there, fully developed, just 600 million years after the Big Bang. The numbers don't just challenge our understanding, they completely shatter it. Webb's infrared eyes pierce through cosmic dust and distance like no telescope before it. Its 21-foot mirror captures light that has traveled longer than any photon humans have ever seen. It's a time machine revealing the universe when it was barely 3% of its current age. We expected to see cosmic infancy. Instead, we found cosmic impossibility. The telescope's discoveries have triggered what scientists quietly call a crisis in cosmology. Research teams worldwide are scrambling to explain what should be impossible, as the very foundation of how we understand the universe's beginning begins to crack under the weight of new evidence. Every image Webb sends back forces us to face a disturbing truth. The story we've told about cosmic evolution, the tale that won Nobel Prizes and filled textbooks, might be fundamentally wrong. We built this telescope to write the final chapter of the universe's origin story. Instead, it's showing us that we might not even have the first page right. Webb was supposed to be our ultimate validator, the instrument that would silence any remaining doubts about the Big Bang. But instead, it has become our greatest challenger, revealing a universe that refuses to follow the rules we've spent decades creating. And this is only the beginning of what Webb has shown us. The galaxies themselves tell an even more impossible story. 6 red dots appeared in Webb's deep field images, cosmic ghosts haunting the early universe. At first glance, these tiny specks seemed ordinary among thousands of galaxies scattered across Webb's field of view. Then astronomers calculated their distances and ages, and the impossible became undeniable. These 6 objects existed just 500 to 700 million years after the Big Bang, when the universe was still a newborn. Here's what makes this so astonishing. According to every model of galaxy formation we've built, these structures shouldn't exist at all in that era of cosmic history. It's like discovering skyscrapers in a world where only mud huts should stand. The early universe should have been too hot, too chaotic, and too poor in heavy elements for complex star formation. Yet each of these 6 galaxies blazes with the combined light of billions of stars. To put that in perspective, it's like building an entire city in just 1 year using only primitive tools. That's exactly what these galaxies achieved on a cosmic scale, organizing billions of stars into massive structured systems within a time frame our best theories say should be impossible. The research team, led by astronomers from Swinburne University, published their findings in Nature, instantly igniting controversy across the scientific community. These weren't mildly unexpected results. They were a direct challenge to our understanding of how matter behaved in the early universe. The galaxies appeared so mature and organized that they seemed to mock our carefully built timeline of cosmic evolution. Think of galaxy formation as constructing a house. First, you need a foundation of dark matter to shape the framework. Then gas must cool enough to begin forming stars. Finally, those stars must live, die, and scatter heavy elements, paving the way for more complex generations of stars. This process should span billions of years before producing the massive, mature galaxies Webb has uncovered. But the 6 galaxies Webb found seem to have skipped most of these steps entirely. They appear fully formed when the universe should have barely cooled from its initial fireball. It's as if someone fast-forwarded through the first few billion years of cosmic evolution, compressing eons of slow development into a single cosmic instant. And the mystery only deepens when we examine just how massive these impossible galaxies truly are. The numbers reveal something that shakes the very foundation of physics itself. One of Webb's galaxies contains over 100 billion times the mass of our Sun. To understand how staggering that is, consider that our own Milky Way holds about 60 billion solar masses of stars, and it's had over 13 billion years to accumulate them. These early universe giants achieved even greater mass in only a fraction of that time. The Milky Way is like a great oak tree that has taken centuries to grow. Its roots deep, its branches sprawling. These early galaxies, by contrast, are like discovering towering redwoods in a garden planted just last week. The comparison exposes how utterly impossible these findings are under our current models of cosmic evolution. Mike Boylan-Colchin from the University of Texas analyzed the implications of these massive early galaxies and reached a troubling conclusion. If the measurements are correct, we're venturing into completely uncharted territory in cosmology. These galaxies are so enormous that we must either rewrite our understanding of galaxy formation or reimagine our understanding of the universe itself. Consider the scale of this dilemma. The most massive of these galaxies contains more stellar material than galaxies that have had billions of extra years to grow and evolve. It's like discovering a 3-year-old child who weighs more than a full-grown adult. The timeline simply doesn't fit with any known process of stellar or galactic development. These galaxies existed when the universe was only 3% of its current age. Imagine compressing your entire adult life into a single year and still managing to learn, build, and create everything within that impossibly short span. That's essentially what these galaxies achieved, on a cosmic scale. Their mass measurements come from analyzing light output and stellar populations. Brighter galaxies contain more stars, and more stars mean greater mass. But these early objects shine so intensely that they imply stellar populations that shouldn't have had time to form, let alone organize into complex structures. Current galaxy formation models predict that creating such massive systems should require at least 2 billion years, even under perfect conditions. Yet these galaxies accomplished the same feat in less than 700 million years. And they did it in the harsh, chaotic environment of the early universe, where star formation should have been far more difficult. The implications reach far beyond these 6 objects. If galaxies could grow this massive this quickly in the early universe, then our entire cosmic timeline needs to be reconsidered. But the mass problem becomes even stranger when you look at how efficiently these galaxies converted gas into stars. For these giants to exist, they would have needed to transform nearly 100% of their available gas into stars, a rate that represents the absolute theoretical maximum of what's physically possible. It's like expecting a factory to operate with perfect efficiency, zero waste, using every atom of raw material in its final product. In today's universe, galaxies typically convert only about 10% of their gas into stars. The remaining 90% is scattered away by stellar winds, supernova explosions, and other violent processes that prevent new stars from forming. Think of it like trying to build a campfire in a storm. Most of your fuel blows away before it can even ignite. And that 10% efficiency isn't a flaw. It's simply how the universe works. It's a fundamental consequence of the physics that governs star formation. When massive stars die in supernova explosions, they release immense energy and material into space, disrupting nearby gas clouds and halting the birth of new stars around them. This creates a natural limit to how efficiently galaxies can turn gas into stars. The early galaxies Webb uncovered would have to break through every one of these natural barriers to star formation. They would need stellar winds that somehow didn't blow gas away. They would need supernova explosions that didn't disrupt the process. They would require a universe that followed completely different physical rules from the one we know today. Reaching near-perfect efficiency would demand conditions existing at the very edge of what's possible under known physics. It's as if these ancient galaxies discovered a way to bend one of the most fundamental limits of cosmic engineering. The gas would have to collapse into stars faster than any disruptive process could. Scatter it. Mike Boylan-Colchin described this efficiency as technically possible, but only if everything in the early universe operated in a dramatically different way than expected. Every mechanism that normally prevents star formation would need to be suppressed or eliminated entirely. Every feedback process that should disrupt stellar growth would have to fail completely. Imagine trying to fill a bucket with water while someone keeps punching holes in the bottom. In normal galaxies, stellar feedback creates those holes, letting most of the gas escape before it can form stars. But these early galaxies would need buckets without holes at all, able to trap and convert every single atom of gas into stars. This efficiency problem exposes something profound about these discoveries. We're looking at galaxies that would have to operate under entirely different physical laws than anything observed elsewhere in the universe. The process of star formation itself would need to be completely redefined. And this mystery deepens when we look at what else these early galaxies contain. At their cores lie objects that challenge our understanding of cosmic evolution even further. At the centers of these impossible galaxies lurk supermassive black holes, each weighing billions of times more than our Sun. Webb has detected these cosmic monsters actively feeding and expanding when the universe was less than 1 billion years old. According to current models of black hole formation, these objects are even more impossible than the galaxies themselves. Black holes grow by consuming matter, but there's a natural speed limit to this process, known as the Eddington limit. Think of it like trying to drink from a fire hose. There's only so much a black hole can swallow before the intense radiation from its own feeding pushes away the rest. This limit acts as a throttle, preventing black holes from growing too quickly. To expand from a stellar mass black hole, born from a collapsing star, to the billion solar mass monsters Webb has revealed should take several billion years, even under ideal conditions. Yet these ancient black holes achieved it in less than 1 billion years, during a time when the universe was far more hostile to such rapid growth. It's like finding a fully grown elephant in a nursery meant only for mice. The timeline simply doesn't match the available time. For this to happen, these supermassive black holes would have to feed continuously, at or near their maximum possible rate, from the very moment the first stars were born. No interruptions, no starvation periods, no competition from other cosmic forces. Webb even discovered a quasar powered by a black hole weighing 10 billion times the mass of our Sun, the most massive black hole ever found in the early universe. This cosmic giant existed when the universe was still an infant, barely old enough to have produced its first generation of stars. The black hole alone contains more mass than most entire galaxies from that era. Their presence creates a cosmic chicken and egg problem. Did the black holes form first, giving birth to the galaxies around them? Or did the galaxies form first, creating the environment that allowed black holes to grow so fast? Either possibility demands processes that move far faster than anything we've ever observed in the modern universe, and these black holes aren't sitting quietly in their galactic centers. They're violently feeding, blazing as quasars, some of the brightest objects in existence. Their accretion releases such extreme energy that it should blow away the very gas needed to keep forming stars in their galaxies. Yet somehow, both the black hole growth and star formation continue at the same time. The discovery of these early supermassive black holes suggests that either our models of black hole formation are fundamentally wrong, or the early universe itself operated under a set of physical laws very different from the ones we know. And the implications become even more astonishing when we examine other mysterious light sources Webb has found in the cosmic dawn. These supermassive black holes are only the beginning of Webb's impossible discoveries, because beyond them, hidden in the deepest reaches of space and time, lie objects even stranger. In the most distant images Webb has ever captured, astronomers found 9 brilliant blue sources of ultraviolet light, shining from a time when stars shouldn't have existed at all. These mysterious beacons come from redshift 25, when the universe was just 100 million years old, a moment when the cosmos should have been dark, silent and empty, still recovering from its violent birth. Yet there they were, blazing in the darkness. This light represents the deepest observation ever made by any telescope, pushing the limits of what we thought was observable. Time. Imagine trying to spot individual candle flames from miles away on the darkest night. Imaginable. That's how precise Webb had to be to detect them. 6 of these objects appeared at redshift 17, roughly 200 million years after the Big Bang. 3 others came from redshift 25, an age so early that no known physics should have allowed stars to exist. Back then, the universe was still too hot, too chaotic for gas to cool and form the first stellar nurseries. The discovery was led by Pablo Pérez González from the Center for Astrobiology in Madrid. His team pushed cosmic observation to its absolute limit, revealing a universe far more active and complex in its first moments than anyone had imagined. The ultraviolet light coming from these sources matches perfectly what astronomers would expect from young, massive, blazing hot stars, which creates a profound mystery. How could such stars exist when the laws of physics say they shouldn't? It's like discovering a roaring bonfire inside a room that's supposed to be too wet and cold for any flame to ignite. Some of these objects appear as tiny points of light, leading scientists to suspect something even stranger than stars. Nearly 30% of them show signs of being primordial black holes, theoretical objects that might have formed in the universe's very first moments, not from collapsing stars, but born directly from the chaos of creation itself. If that's true, they could represent an entirely new pathway for how massive objects form, existing from almost the beginning, serving as ready-made seeds for the first galaxies to grow around. The light from redshift 25 means we're looking at a universe less than 1% of its current age. At that time, atoms had only just formed, and space was still emerging from the opaque fog left behind by the Big Bang. Finding organized sources of light in this era is like walking into an empty concert hall and finding a full orchestra already playing. And these discoveries create yet another problem for cosmology. The universe shouldn't have had enough time to build anything this bright, this structured. According to our current models, forming large galaxies should take at least 2 billion years, even under perfect conditions. But Webb's observations show that somehow, the universe managed to do it in under 700 million years, during the most chaotic period in cosmic history. It's the cosmic equivalent of watching someone run a marathon in the time it takes to sprint 100 meters. This impossible timeline breaks every rule of how we understand cosmic evolution. Dark matter should have needed time to gather, forming the invisible scaffolding for galaxies. Gas should have cooled slowly before condensing into stars. And those first stars needed time to live, die, and enrich space with heavy elements, the building blocks for everything else. Each of these processes takes time. They follow physical laws that can't be rushed. Gravitational dynamics, thermodynamics, nuclear fusion, all unfolding at fixed cosmic speeds. Yet somehow, the early universe didn't wait. It raced ahead, lighting the first fires in a cosmos that shouldn't have been ready to burn. Think of galaxy formation like cooking a complex meal, a process that demands patience and precision. Every step must be done in order. You can't skip preparation, you can't rush the cooking, and mixing the wrong ingredients too soon ruins the result. Yet somehow, the universe seems to have prepared this cosmic feast in a fraction of the time the recipe allows. The 700 million year window available to Webb's early galaxies becomes even more astonishing when you consider the hostile conditions of the young universe. Gas was far hotter, making star formation harder. The universe was denser, more turbulent and chaotic, and heavy elements were almost non-existent, limiting the types of stars that could even form. Under such extreme conditions, galaxy formation should have taken longer than the usual 2 billion year minimum, perhaps 3 or 4 billion years. Instead, Webb found fully formed, massive galaxies that had somehow overcome every obstacle, every physical limit, every timeline constraint that should have made their existence impossible. Cosmologist Catherine Nelson described the issue clearly. Our cosmological theory predicts that galaxies of this mass should take much longer to assemble. This isn't a small mismatch that can be brushed aside as a measurement error. It's a threefold difference between what we predict and what Webb actually sees. And this time problem doesn't end with a few galaxies. If the universe was able to create such massive structures so quickly, then our entire understanding of cosmic evolution may need to be rewritten. The carefully built timeline of the cosmos, supported by decades of theory and observation, begins to crumble under the weight of Webb's discoveries. And this paradox only deepens when we turn to another great cosmic mystery: the rate of the universe's expansion itself. The universe is expanding, yes, but astronomers can't agree on how fast. This conflict, known as the Hubble tension, has become one of the most serious crises in modern cosmology. Different ways of measuring the expansion give different answers, and the gap is too big to ignore. When astronomers measure the local universe using nearby supernovae and other cosmic landmarks, they find an expansion rate of about 73 kilometers per second per megaparsec. But when they calculate it from the cosmic microwave background, the ancient light from the early universe, they get about 67 kilometers per second per megaparsec. That 6-unit difference may sound tiny, but it's not. It's far too large to be caused by random error. Imagine using 2 rulers to measure the same object, and one always says 10 inches, while the other insists it's 11. If both are perfectly calibrated, then something must be wrong, not with your tools, but with your understanding of what you're measuring. The Hubble tension has haunted cosmology for over a decade, despite increasingly precise data from independent research teams. Now, Webb's new measurements have confirmed the higher expansion rate, eliminating the possibility that earlier results were caused by flawed instruments or biased observations. Adam Rees, who won the Nobel Prize for discovering the universe's accelerating expansion, led the latest Webb analysis, using the telescope's largest data sample yet, spanning its first 2 years. His team confirmed that the local universe is expanding faster than early universe models predict. This creates a temporal paradox, compounding the timeline problem already revealed by Webb's early galaxies. If the universe truly expanded faster in its youth, it could explain why structure formed so quickly. But that explanation would demand new physics, something beyond our current understanding, to explain why the rate changed so dramatically over time. Some scientists propose that an unknown form of early dark energy briefly accelerated expansion after the Big Bang. Others suggest exotic particles, shifting physical constants, or primordial magnetic fields that may have operated differently in the early cosmos. Mark Kamiankowski of Johns Hopkins University believes solving the Hubble tension could unlock deeper insights into the other discrepancies now plaguing the standard model of cosmology. The expansion problem and Webb's discovery of massive early galaxies might actually be connected, both pointing toward a missing piece of physics. In our cosmic story, the Hubble tension isn't just a debate over numbers. It's a sign that our entire picture of cosmic time and evolution may be incomplete, or even wrong. And when we combine this expansion paradox with Webb's impossible galaxies, we see a universe that refuses to follow the rules we've written for it. But the mystery doesn't stop there. The structure of these early galaxies makes the paradox even deeper. They aren't chaotic clumps of matter. They're organized, structured, and astonishingly refined. The early universe should have been a turbulent place, gas and dust only beginning to clump together under gravity's pull, yet Webb's images reveal a cosmos already displaying pattern and order, galaxies shaped like flattened disks and elongated tubes, not the irregular blobs astronomers expected. A level of cosmic sophistication that, by all accounts, simply shouldn't have existed yet. It's like discovering that a chaotic construction site, scattered with random building materials, has somehow organized itself into neat rows of completed houses, all while no one was watching. These orderly cosmic structures shouldn't exist this early. They require time, stability, and countless gravitational interactions to emerge. In today's universe, galaxies develop their shapes over billions of years through collisions, mergers, and gradual evolution. But the galaxies Webb uncovered already display that same mature sophistication when the universe was barely old enough to form its first stars. Think of galaxy formation as choreographing a complex dance. In the early universe, the dancers should still be stumbling, bumping into one another as they learn the basic steps. Yet Webb's observations reveal cosmic dancers performing with perfect rhythm, as if they've been practicing for eons. This level of structure requires what cosmologists call dynamical relaxation, a process in which countless gravitational interactions slowly smooth and organize matter into the elegant shapes of mature galaxies. It's a process that unfolds over immense stretches of time, through millions of orbital cycles and encounters, and yet, somehow, these galaxies achieved that harmony almost immediately after the cosmic dawn. Astronomer Simon Lilly from ETH, Zurich found that some of these early galaxies had already carved out enormous bubbles of ionized gas, stretching nearly 2 million light-years across. These vast regions represent another form of large-scale order that requires coordination across cosmic distances. To create such bubbles, countless stars must ignite together, releasing torrents of ultraviolet radiation that sweep away surrounding gas, clearing transparent pockets in what should have been a dense, opaque universe. Coordinating this process across millions of light-years implies a level of organization that directly contradicts our picture of the early cosmos as chaotic and turbulent. It's like discovering that a newborn baby can already speak fluently and solve complex math problems. The smooth, structured galaxies Webb found suggest two startling possibilities. Either the early universe was far more mature and stable than we believed, or the laws governing structure formation allow things to happen much faster than our physics. Predicts both possibilities demand a fundamental rewrite of our understanding of how the universe evolves, and the mystery only deepens. When we look at the physical conditions these galaxies had to form under, the early universe was anything but welcoming. Gas temperatures were scorchingly hot, conditions that should have made galaxy formation nearly impossible. Before gravity can gather matter into stars, that gas must cool down dramatically. But Webb's massive early galaxies somehow emerged, even while the universe was still blazing hot. Imagine trying to build a snowman during a heat wave. When the temperature is over 100 degrees Fahrenheit, the snow melts faster than you can shape it. That's what early galaxy formation faced in a universe where gas temperatures were thousands of degrees hotter than they are today. Hot gas resists gravity's pull. The faster the gas particles move, the harder it becomes to compress them into the dense clouds needed to form stars. This thermal pressure creates a fundamental barrier, a cosmic standoff between heat and gravity that should have delayed galaxy formation by billions of years. Astrophysicist Alison Kirkpatrick from the University of Kansas explains, galaxies can't form quickly in the early universe because the gas is simply too hot. That heat prevents it from collapsing into stars and galaxies. The cooling process that eventually lowers those temperatures happens slowly in an expanding universe. As space itself stretches, it carries heat away, allowing temperatures to drop only gradually over time. This cooling has a built-in timeline, a physical speed limit that can't be bypassed without rewriting the laws of thermodynamics. For Webb's galaxies to exist, the gas must have either cooled much faster than physics allows, or stars must have somehow formed at temperatures far higher than any observed today. Both scenarios defy our understanding of stellar formation, and the physics that govern heat and gravity and the temperature problem is only half the story. The early universe was also much denser, meaning gas particles collided far more often, generating additional heat and resisting the cooling process even more. The early cosmos was essentially a pressure cooker, one that should have prevented, not encouraged, rapid galaxy growth. Some theories suggest that dark matter may have played a crucial role, forming invisible scaffolds that helped gather and cool normal matter more efficiently. But even this process requires time for dark matter to clump together, adding yet another layer of delay to an already impossible timeline. The combination of intense heat, high density, and hostile conditions should have stopped galaxies from forming so early. And yet Webb has revealed massive, organized galaxies thriving in exactly those impossible conditions. The conclusion is unavoidable. Either our understanding of early universe physics is incomplete, or these galaxies were born through processes we haven't yet discovered. This temperature problem leads directly into another cosmic riddle, the role of dark matter itself, and how it shaped the invisible framework that allowed the first structures to rise from chaos. Dark matter makes up nearly 85% of all matter in the universe, forming the invisible gravitational framework that shapes normal matter into galaxies and cosmic structures. This unseen scaffolding should have taken billions of years to fully develop. Yet, the galaxies observed by Webb appear to have formed long before dark matter had enough time to lay that foundation. Think of dark matter as the steel skeleton of a skyscraper, It must be built first before you can add walls, floors, and windows. In the universe's grand construction project, dark matter halos are that essential framework. They define where galaxies will form, how large they'll become, and how they'll evolve. But there's a problem. Dark matter interacts only through gravity. It can't radiate away energy like normal matter can, so it clumps together slowly, over cosmic timescales measured in billions of years, not the mere hundreds of millions that existed when Webb's galaxies appeared. Dark matter halos form hierarchically. Tiny clumps emerge first through gravitational instabilities. Over time, these merge into larger halos, which eventually become massive enough to attract gas and form the first stars and galaxies. But for Webb's enormous early galaxies to exist, they would need halos containing trillions of solar masses worth of dark matter, structures that should take billions of years to form. Even in the most optimistic scenarios, the math doesn't work. The universe simply hadn't existed long enough for such massive halos to develop. As astrophysicist Alison Kirkpatrick explains, galaxies aren't supposed to form so quickly. Dark matter must first create the deep gravitational wells that funnel gas inward to form stars. That process comes with built-in delays that cannot be bypassed without rewriting the basic rules of physics. This dark matter timeline problem suggests one of two possibilities. Either these ancient galaxies formed through a completely different mechanism than what we see today, or dark matter behaved differently in the early cosmos than our models predict. Both options demand major revisions to our understanding of fundamental physics. Some scientists have proposed that primordial black holes might have served as instant gravitational seeds, skipping the slow dark matter phase entirely. But if true, that would mean exotic new physics must have shaped the universe's very first moments, far beyond what the standard model allows. And this scaffolding issue doesn't stop at individual galaxies. The vast cosmic web, the network of dark matter filaments linking galaxies across immense distances, should also have taken billions of years to form. Yet Webb's data hints that this large-scale structure was already in place far earlier than expected. All of this raises a deep contradiction. The invisible backbone of the cosmos seems to have assembled itself much faster than the laws of physics should permit. But the mysteries don't end there. Webb's discoveries challenge not just the structure of early galaxies, but also their chemical makeup. The telescope has detected heavy elements like carbon, oxygen, and even iron in galaxies that existed when the universe should have contained nothing but hydrogen and helium. These complex elements are forged inside stars through nuclear fusion and scattered into space by supernova explosions. Their presence in such early galaxies creates a chemical timeline paradox. After the Big Bang, the universe produced only hydrogen, helium, and a trace of lithium. Everything heavier, every element that makes up planets. Life, and even us, had to be built later inside stars, over long cycles of birth and death. It's like walking into a kitchen, stocked only with raw ingredients, and somehow finding a gourmet meal already prepared. Creating these heavier elements requires multiple generations of stars. The first, called Population 3 stars, formed from pristine hydrogen and helium. They lived short, brilliant lives, exploding as supernovae and seeding the cosmos with the first traces of heavier elements. The next generations formed from that enriched material, continuing the process of chemical evolution. But this takes time, millions of years per stellar life cycle, and billions overall for the levels of heavy elements that Webb now sees. The mixing of supernova material throughout a galaxy's gas is slow and gradual. Yet Webb's observations show galaxies that appear to have skipped several steps in that process. The detection of iron is especially shocking, because it forms only in the cores of massive stars, moments before they collapse into black holes or neutron stars. For that iron to be spread throughout an entire galaxy, multiple generations of stars and supernovae must have already occurred. Spectroscopic data from Webb doesn't just show trace amounts of these elements, it shows abundances that suggest mature, chemically evolved galaxies. The fingerprints of these elements point to a history of complex nucleosynthesis that should have taken billions of years. Some of these early galaxies even show evidence of cosmic dust, tiny solid particles formed from heavy elements in the cold spaces between stars. And that dust formation is another sign of unexpected chemical maturity in a universe that, by all accounts, should still have been in its infancy. Dust formation adds yet another layer of complexity to this chemical mystery. It doesn't just require the presence of heavy elements. It also demands the perfect environmental conditions for those elements to bind into solid grains. The rapid chemical evolution revealed by Webb suggests that either the very first stars were far more massive and short-lived than we believed, or that the nuclear processes forging heavy elements worked much faster in the early cosmos than our physics allows. Either possibility forces major revisions to our understanding of stellar evolution and nucleosynthesis. This chemical timeline problem stacks on top of every other impossibility Webb has exposed. These galaxies would have needed time to form their dark matter halos, time to cool their scorching gas, time to birth multiple generations of stars, time to forge and spread heavy elements, and time to organize into intricate structures. But the universe simply hadn't existed long enough for all these events to unfold. This unexpected chemical maturity ties directly to another one of Webb's astonishing discoveries: how these early galaxies interacted with their surrounding cosmos, creating yet another timeline paradox. Webb found that early galaxies were powerful enough to clear out enormous regions of space around them, ionizing gas across millions of light years, and carving transparent bubbles in what should have been an opaque early universe. This process, known as cosmic reionization, should have taken hundreds of millions of years to complete. Yet, Webb shows it happened far faster than theory predicts. After the Big Bang, the universe entered a period known as the Dark Ages, when space was filled with neutral hydrogen that trapped light. It was like trying to see through a thick fog that absorbs and scatters every photon, making the young cosmos opaque. For light to travel freely, that fog had to be burned away through ionization, a process where ultraviolet radiation strips electrons from hydrogen atoms, transforming the gas into transparent plasma. Early galaxies produce that radiation through their bright, hot, young stars. But here's the paradox. The energy needed to clear regions millions of light years wide should have required far more time and far more galaxies than Webb actually observes. Simon Lilly's team found that even small, primitive galaxies were somehow creating ionized bubbles up to 2 million light years across. To grasp that scale, imagine a single house producing enough light to illuminate an entire state. The power required for that level of ionization should have demanded galaxies many times larger, or countless smaller galaxies working together. Eventually, these transparent bubbles merge to create the fully clear universe we see today. But according to standard models, that merging process should have taken hundreds of millions of years. Yet, Webb's data shows the reionization process nearly complete when the universe was just 1 billion years old, far earlier than expected. This compressed timeline means early galaxies were either far more numerous, far more massive, or far more efficient at producing ionizing radiation than our physics allows. The reionization paradox creates another impossible demand for efficiency. These galaxies had to convert their gas into stars fast, enough to generate extreme ultraviolet radiation, while also growing massive enough to power the ionization of their surroundings, all while forming the complex internal structures Webb observed. And here's another limit. Each ionizing photon can free only one hydrogen atom. That means the total energy required for reionization is not infinite. It's calculable and enormous. To meet that demand, early galaxies would have needed to produce far more ionizing photons per unit of stellar mass than any galaxies do today. This suggests either the stars back then were fundamentally different, or that the early universe somehow produced energy with greater efficiency. Webb's discovery of rapid reionization paints a picture of an early universe far more active, violent and energetic than we ever imagined. Massive galaxies, accelerated star formation, and large-scale ionization all appear to be happening at speeds that defy our current understanding of cosmic physics. This reionization timeline problem becomes the final link in a chain of impossibilities, an interconnected web of mysteries that can't be solved by tweaking our existing models. Instead, they hint that the early universe itself might have operated under entirely different physical rules than the cosmos we know today. But perhaps there's another explanation. What if the massive black holes Webb discovered didn't grow from the collapse of stars, but existed from the very beginning? These so-called primordial black holes represent one of the most radical alternatives in modern cosmology. They could explain how massive structures formed so quickly without breaking the laws of physics. Unlike stellar black holes, which are born from dying stars, Primordial black holes could have formed directly from the extreme energy fluctuations during the universe's first fractions of a second. If they existed, they would have acted as ready-made gravitational anchors, allowing galaxies to form rapidly, bypassing the slow construction of dark matter halos entirely. Think of stellar black holes as oak trees, growing slowly from tiny acorns over time. Primordial black holes, by contrast, would be like discovering fully grown sequoias that somehow appeared mature from the very beginning of the forest. They seem to have skipped the entire cosmic growth process, existing right from the dawn of time, ready to start pulling in matter and constructing galaxies around themselves. According to Pablo Perez Gonzalez and his team, around 30% of the mysterious early light sources detected by Webb match the characteristics of primordial black holes rather than young stars. These objects appear as sharp point-like sources instead of extended regions, implying they could be individual massive black holes rather than clusters of newborn stars spread across galaxies. If primordial black holes acted as the gravitational seeds for early galaxy formation, they might explain many of Webb's so-called impossible discoveries. In this scenario, massive early galaxies wouldn't need to wait billions of years for dark matter halos to slowly assemble. Instead, they could start forming immediately around these ready-made gravitational wells. Primordial black holes could also account for the rapid chemical enrichment that Webb observed in the first galaxies. These ancient objects would have quickly begun swallowing nearby gas, igniting bursts of star formation in their surroundings. The resulting stars would live short, intense lives, burning hot, exploding as supernovae, and spreading heavy elements into space, far faster than conventional models predict. The intense accretion process around these black holes releases vast amounts of energy, which could explain the extraordinary brightness of the earliest cosmic sources Webb detected. That same energy might also have ionized surrounding gas, helping to carve out the enormous, clear regions of space visible around those early galaxies. However, the existence of primordial black holes requires extremely fine-tuned conditions during the universe's very first moments. The early cosmos would have needed much larger density fluctuations than standard models allow, hinting at exotic physics during inflation, the split-second expansion after the Big Bang. The primordial black hole idea also makes testable predictions. These objects should leave identifiable signatures in the cosmic microwave background and create distinct patterns in the large-scale structure of the universe, setting them apart from normal dark matter-driven formation. Yet primordial black holes are only one possible explanation for Webb's cosmic anomalies. Other theories go even further, challenging the very concept of universal expansion. One of these is the tired light theory, first proposed by astronomer Fritz Zwicky in the 1920s. It suggests that light doesn't appear redshifted because galaxies are racing away from us, but because photons lose energy as they travel across the vast cosmic distances. In this model, the universe might not be expanding at all. According to tired light, photons gradually shed energy, stretching into longer, redder wavelengths the farther they travel. Imagine a marathon runner starting at full speed but gradually tiring over the course of the race. The light begins its journey energetic and blue, but by the time it reaches us, it's slower and redder. This energy loss could happen through interactions with the quantum vacuum, cosmic dust, or other unknown processes operating over unimaginable distances. Even Einstein once suggested that light might lose energy in proportion to the distance it travels, though he never specified how. Intriguingly, Webb's latest data have revived interest in the tired light model, as some of its findings seem to fit its predictions better than the expanding universe model. Lior Shamir of Kansas State University analyzed redshift data from more than 30,000 galaxies and discovered patterns that align more closely with tired light than with cosmic expansion. If this theory is correct, many of the timeline paradoxes Webb uncovered disappear. The universe wouldn't need to be only 13.8 billion years old. It could be much older, perhaps even eternal. That extra time would easily allow for the natural formation of massive galaxies and supermassive black holes, removing the need for impossible early universe speeds. In such a universe, the massive galaxies Webb sees at extreme redshifts wouldn't be newborns formed in record time. They'd be ancient, mature systems, their apparent youth merely an illusion caused by misinterpreting redshift as evidence of expansion instead of energy loss. The tired light theory also offers a striking solution to the Hubble. Tension, the long-standing disagreement between measurements of the universe's expansion rate. If the universe isn't expanding at all, there's no expansion rate to measure, and the conflict vanishes. Shamir's research even found that galaxies rotating in opposite directions relative to the Milky Way display different redshift patterns, likely reflecting Earth's motion through space rather than any universal recession. This subtle asymmetry strengthens the tired light case and challenges one of the core assumptions of modern cosmology, that cosmic redshift must mean the universe is expanding. However, the tired light theory faces serious challenges when compared with other astronomical evidence. The cosmic microwave background radiation, the abundance of light elements, and the large-scale structure of the universe all strongly support the Big Bang model with cosmic expansion. Reconciling tired light with these well-established observations requires additional, and often speculative, modifications. One of its biggest problems lies in time dilation, the observed slowing of distant supernova explosions. These cosmic events unfold more slowly at higher redshifts, precisely as predicted by an expanding universe. Tired light models have great difficulty reproducing this effect without introducing new, unverified physics. Despite these challenges, Webb's groundbreaking discoveries have shaken cosmology to its core, forcing scientists to re-examine the very foundations of cosmic redshift and expansion. The massive early galaxies and impossible formation timelines revealed by the telescope suggest that our understanding of cosmic history may require a radical rewrite. Even more astonishing, Webb has uncovered evidence of active star formation taking place when the universe was just 100 million years old, a time when the cosmos should have been too hot, dense and chaotic for stars to exist at all. In this era, matter had only recently cooled from the inferno of the Big Bang. The universe's gas remained blisteringly hot and evenly spread, while the heavier elements necessary for star formation had not yet been forged. Under such extreme conditions, the birth of stars should have been virtually impossible, like trying to light a campfire during a hurricane with soaking wet wood and no spark. Hot gas resisted gravitational collapse, turbulence prevented stable cloud formation, and the absence of metals, which aid in cooling, made condensation even harder. For a star to form, a gas cloud must cool and compress under its own gravity until its core reaches about 10 million degrees, hot enough for nuclear fusion to ignite. But in the early universe, the surrounding gas was already near that temperature, making cooling, and thus star formation, extremely difficult. The first generation of stars, known as population 3 stars, were expected to be vastly different from modern ones. Composed purely of hydrogen and helium, they would have been enormous, hot and short-lived, burning out in just a few million years. This should have caused a natural delay before the universe could form large, stable populations of stars. Yet Webb's observations tell a different story. The telescope has detected brilliant ultraviolet light from massive young stars shining at redshift 25, far earlier than standard models predict. This suggests that star formation began much faster and more efficiently than previously thought. Some research teams propose that early star formation followed a bursty pattern, short, intense waves of starbirth followed by long dormant phases. During these bursts, galaxies could form stars at extraordinary rates, temporarily overcoming the hostile conditions of the early cosmos. Astrophysicist Claude-André Faucher-Giguère of Northwestern University suggests that these galaxies experienced rapid starbursts after long periods of inactivity, producing the bright, massive stellar populations Webb has now captured. In this model, stellar winds and supernova explosions periodically cleared gas from galaxies, pausing star formation. When the gas cooled and fell back in, it triggered another explosive round of stellar birth, a kind of cosmic heartbeat pulsing across deep time. However, even the bursty formation model struggles to account for the sheer number and luminosity of early stars that Webb observed. The energy output from these ancient stellar populations exceeds even the most optimistic predictions, hinting that the laws of stellar physics themselves may have operated differently in the early universe. This rapid, large-scale star formation adds yet another piece to the growing timeline puzzle, demanding not only accelerated galaxy assembly, but also faster stellar evolution. capable of producing heavy elements and intense radiation within impossibly short timescales. All of this directly challenges the foundation of modern cosmology, the lambda cold dark matter, LCDM model. This framework, built on dark energy, cold dark matter, and conventional physics, has successfully explained the structure and evolution of the cosmos for decades. But Webb's findings now represent its greatest test yet. The LCDM model makes precise predictions about how quickly galaxies, stars, and large-scale structures should form. These are grounded in fundamental physics: how dark matter clusters, how gas cools, and how gravity shapes the cosmos over time. Webb's data violates nearly all of these predictions. Think of the Standard Model as a meticulously crafted recipe, one that specifies exactly how long each step should take to produce the final cosmic dish. Webb, however, has found a universe that's already finished cooking. Long before the timer even started, the Standard Model of cosmology describes the universe like a meticulous recipe, one that requires billions of years of slow simmering to build complexity, structure, and life as we know it. Yet Webb's observations suggest that somehow the cosmos managed to prepare a gourmet meal in mere minutes, using only the simplest ingredients and a cosmic microwave instead of a slow cooker. Astrophysicist Mike Boylan-Colchin warned that if Webb's mass measurements are confirmed, then fundamental revisions to modern cosmology will be unavoidable. These aren't small tweaks or corrections. They demand a complete rethinking of how the universe forms and evolves. According to the lambda cold dark matter, LCDM model, only a tiny fraction of the universe's matter should have assembled into massive galaxies during the first billion years after the Big Bang. But Webb has revealed roughly twice as many massive galaxies as this model allows, with some individual objects 10 times heavier than theory says they could possibly be at that time, and this contradiction doesn't stop at galaxy mass. It extends across formation timescales, chemical evolution rates, and galactic organization, forming a consistent pattern of violations across multiple independent observations. It's not a single anomaly. It's a systematic breakdown of the framework that has defined cosmology for nearly a century. The situation is made worse by the fact that LCDM is not a loose set of ideas, but a tightly interlinked web of equations and dependencies. Changing one part to explain Webb's discoveries inevitably creates conflicts elsewhere. For example, modifying dark matter properties to accelerate structure formation could explain early galaxies, but it would also disrupt the cosmic microwave background, distort the large-scale structure of the universe, and conflict with the predicted abundances of light elements formed during the Big Bang. Likewise, altering the universe's expansion rate to buy more time for early formation would throw off our age estimates of ancient stars, the timing of reionization, and the distance redshift relationship that underpins modern observational cosmology. Nobel laureate James Peebles, one of the architects of modern cosmology, reminds us that science thrives on doubt, and that Webb's findings should be seen as an opportunity for progress, not a crisis. Yet, the scale and scope of these violations suggest that incremental adjustments won't be enough. The cosmos may be forcing us toward a fundamental reimagining of our place in it. This growing crisis doesn't just challenge our theories. It strikes at the very methods of observation and measurement that astronomers have refined for decades. Webb's data implies that even our most basic assumptions about interpreting cosmic light might be flawed. One of the most striking examples is what's now being called the angular size anomaly. Webb discovered that distant galaxies appear much larger in the sky than the expanding universe model predicts, a direct challenge to one of the core assumptions of the Big Bang framework. In an expanding cosmos, there's a specific relationship between an object's distance, true size, and apparent angular size. Imagine a toy soldier painted on a balloon. As the balloon inflates, the soldier moves farther away and appears smaller, even though he hasn't changed in size. That's how galaxies should appear in an expanding universe. The farther they are, the smaller they should look. But Webb's data doesn't agree. Distant galaxies appear roughly 10 times larger than Big Bang models predict at their measured redshifts. This discrepancy is not a statistical fluke. It's systematic, consistent, and verified across multiple independent measurements. The angular size problem connects directly to the tired light hypothesis, which proposes that redshift results from energy loss over distance, not from expanding space. If that interpretation is correct, then the relationship between distance, redshift, and angular size would change completely, and would, in fact, align far better with Webb's observations. Biblical cosmologist Danny Faulkner analyzed Webb's angular size data and found that high redshift galaxies average around 0.22 arc-seconds, exactly what non-expanding Doppler models predict, and about 10 times larger than Big Bang expectations. This makes it one of the most precise observational tests of cosmic expansion ever performed. What makes this measurement so powerful is its simplicity. It doesn't rely on assumptions about dark matter, star populations, or galaxy evolution. It's pure geometry, light, distance, and basic trigonometry, testing whether space itself is truly stretching over time. If space is not expanding, then the cause of cosmic redshift must lie elsewhere. Perhaps in tired light, intrinsic redshift, or some unknown physical process that doesn't require the fabric of the universe to stretch. Such a possibility would also eliminate the need for dark energy, the mysterious force thought to drive the universe's accelerating expansion. The angular size anomaly also affects brightness. Distant galaxies appear brighter than expanding universe models predict. Together, these two observations, larger sizes and higher brightness, form a coherent pattern that supports static universe interpretations while directly challenging the foundations of expansion-based cosmology. These geometric measurements are among the cleanest, most direct tests of cosmic expansion ever made, free from the complex astrophysical assumptions that cloud so many other observations. And yet, they consistently contradict expansion predictions, suggesting that something fundamental about our understanding of space, time, and the universe itself may need to be rewritten. The angular size crisis doesn't just affect single galaxies. It shakes the very foundation of how we understand space, time, and the geometry of the cosmos itself. Webb's discoveries have revealed anomalies that reach deep into the timeline of cosmic evolution, hinting that the universe's history may be completely different from what we've believed for decades. According to the Big Bang model, the universe should have gone through a long, dark era lasting hundreds of millions of years, a period with no stars, no light, and no galaxies. But Webb's observations suggest those so-called dark ages may never have happened. Instead, the universe seems to have lit up and begun forming stars and galaxies far earlier than theory ever allowed. In standard cosmology, the Dark Ages begin about 400,000 years after the Big Bang, when the universe cools enough for electrons and protons to combine into neutral hydrogen, a process called recombination. This event made space transparent for the first time, but also removed the free electrons needed to sustain electromagnetic energy production. With no new light sources, the cosmos should have fallen into silence, a vast, cold darkness where only gravity worked to slowly gather matter into the first structures. That darkness was expected to last until the first stars ignited hundreds of millions of years later, marking the dawn of light. Think of it like a city-wide power outage, a long blackout before electricity is finally restored. But Webb found bright, organized galaxies shining at redshift 25, when the universe was only about 100 million years old. That means the cosmic dawn arrived 3 to 4 times earlier than predicted, compressing the Dark Ages into a brief moment, or erasing them entirely. Active star formation at redshift 17 and beyond indicates the universe never entered a prolonged dormant phase at all, instead of a quiet, lifeless cosmos. Webb reveals a universe that became luminous and dynamic almost immediately after. Recombination. Astrophysicist Emma Chapman of the University of Nottingham noted that finding massive galaxies so soon after the Big Bang suggests the Dark Ages may not have been so dark after all. The early universe appears to have been flooded with our starlight much sooner than expected, while discovery that fundamentally reshapes our cosmic timeline. The disappearance of the Dark Ages removes one of the key pillars of Big Bang cosmology, suggesting that the early universe operated under physical laws very different from what we've assumed. The rapid leap from recombination to intense star formation defies the slow, gravitational buildup predicted by standard models. If the Dark Ages truly never existed, the timeline problems surrounding early galaxy formation become even more severe. The universe would have had even less time to assemble the massive, organized systems that Webb observes. This revelation also rewrites our understanding of cosmic reionization. the process that made the universe transparent to most wavelengths of light. If stars began forming earlier, ionization must have begun earlier too, demanding a total revision of how we chart cosmic transparency. Such early activity implies one of two things. Either the conditions immediately after recombination were vastly different than we believe, or there were alternative sources of energy, beyond ordinary stars, illuminating the young cosmos. The disappearance of the Dark Ages is yet another fundamental blow to Big Bang predictions, adding to a growing list of cosmic processes that seem to happen faster, earlier, and far more efficiently than our models allow. But Webb's revelations don't stop there. The telescope captured enormous galaxies from the universe's infancy. Galaxies showing clear signs of recent mergers and ongoing galactic cannibalism. These are processes that should take billions of years to unfold, yet Webb sees them happening almost instantly in the young cosmos. Galactic mergers are among the most violent and complex events in nature, requiring a delicate gravitational choreography as two massive systems spiral together over hundreds of millions of years. The stages are precise, from initial, attraction and orbital decay to tidal disruption and final, fusion into a single giant structure. Imagine two vast cities, growing toward one another over centuries until they merge into one sprawling metropolis. That's how slow these events should be. But Webb found cosmic cities that seem to have merged overnight, in a universe barely old enough for neighborhoods to form. The galaxies Webb observed show warped shapes, stretched structures, and chaotic forms, all clear signatures of recent mergers. These gravitational distortions mean the galaxies must have interacted over long periods and completed highly complex processes within a shockingly short cosmic window. According to current theory, such major mergers should have been extremely rare in the early universe. Galaxies would have been small, widely separated by expansion, and lacking the mass needed to pull each other together. The merger process itself also adds significant time, making Webb's observations even harder to explain. And yet, the telescope reveals not just a few collisions, but a pattern: widespread galactic cannibalism across the early cosmos. Large galaxies appear to be devouring smaller ones, rapidly growing through accretion in ways that defy the expected timeline. This hyperactive merger activity could help explain why early galaxies became so massive so fast. But it also deepens the paradox. For these giant galaxies to exist, smaller ones must have formed first to serve as building blocks. But those galaxies too would have needed time to form. The problem runs even deeper. The gravitational physics that govern mergers are fixed. Orbital speeds, tidal forces, and dynamical friction all obey precise physical laws that can't be simply sped up. Yet Webb's cosmic snapshots suggest that somehow the universe found a way to fast forward through these monumental processes, rewriting the rhythm of cosmic evolution itself. Webb's observations of galactic mergers hint at something extraordinary. Either gravity itself worked far more efficiently in the early universe, or the original distribution of matter was completely different from what modern cosmology predicts. Both ideas demand deep revisions to our understanding of how cosmic structures form and evolve. These rapid galactic collisions didn't just reshape galaxies, they ignited enormous bursts of star formation, releasing intense waves of energy that could help explain the impossible brightness Webb detected in the earliest galaxies. Each merger acted like a cosmic spark, triggering powerful starbursts that briefly illuminated the young universe. But they also add a new layer of complexity to the already impossible cosmic timeline. The abundance of early mergers revealed by Webb paints a picture of a far more chaotic and energetic young cosmos, one filled with massive gravitational interactions happening at speeds current physics can't account for. This accelerated cosmic violence connects directly to another major mystery: the extreme brightness of early galaxies, whose luminosity seems to defy the very laws of physics. Webb has found galaxies so bright that they violate fundamental limits of energy production in stars. These ancient systems shine with a brilliance that shouldn't be physically possible, as if the universe was generating light faster and more efficiently than nature allows. Normally, a star's brightness depends on its mass. The largest stars burn their nuclear fuel at the fastest possible rates, but their output is capped by strict physical boundaries. Push beyond them, and fusion itself breaks down. When billions of stars are grouped into a galaxy, their total light output should follow predictable limits based on these rules. Yet Webb has observed galaxies exceeding these limits by factors of 10 or more, meaning their stars must be far more massive, more efficient, or powered by energy sources completely unknown to modern physics. Think of it like a light bulb. No matter how advanced, there's a maximum wattage it can handle before it burns out. These early galaxies are like cosmic light bulbs glowing, far beyond that limit, suggesting either new physics or an entirely different kind of power source. What makes this discovery even more puzzling is that the first generation stars should have been less efficient at producing light, not more. In the early universe, the gas clouds lacked heavy elements, materials that help modern stars shine more brightly. This means the earliest stars should have been dimmer, not dazzlingly bright. But Webb's galaxies glow with such intensity that they seem to contain stars larger than theoretical limits, fusion processes running more efficiently than allowed, or completely different mechanisms of energy generation. Some scientists have suggested that supermassive black holes at galactic centers could be contributing to this immense brightness, feeding on surrounding matter and radiating energy. But those same black holes present another paradox. Their feeding processes should actually reduce brightness by releasing powerful feedback that disrupts nearby star formation, not amplify it. This brightness crisis doesn't stop with individual galaxies. It extends to the entire universe. If early galaxies were truly this luminous, their combined light should have created a glowing cosmic background visible even today. But we don't see that glow. The absence of this excess background light means one of three things must be true. Our distance measurements are wrong, unknown processes are absorbing the light, or the brightness itself points to new, unrecognized physics at work. The extreme luminosity also affects another key chapter of cosmic history: reionization. The excess radiation from these bright early galaxies could explain why the universe became transparent so quickly. But that solution creates new problems, because it requires energy, production mechanisms that go far beyond what physics allows. Astrophysicist Claude-André Faucher-Giguère has proposed that bursty star formation might account for the extreme brightness, short, violent periods where galaxies briefly shine far above average. Yet even these models can't fully explain the sustained luminosity Webb observes across multiple cosmic epochs. These violations of brightness limits pose some of the most direct challenges to stellar physics ever seen. Unlike other cosmological puzzles that can be adjusted with ideas like dark matter or modified gravity, this one hits the foundation of how stars produce light. The energy production crisis has pushed physicists to explore radical new possibilities, perhaps unknown forces or exotic. Particles once existed in the early universe, changing how matter interacted and how light was born. It suggests that the young cosmos may have operated under physical laws completely different from those that govern the universe today. To explain Webb's impossible findings, scientists are now proposing entirely new forms of physics, invisible forces and particles that could have existed in the first moments after the Big Bang, only to vanish as the universe evolved. These ideas represent an attempt to preserve our cosmic timeline by rewriting the fundamental rules of reality itself. As astrophysicist Mike Bohlen-Colchin noted, one of the most extreme possibilities is that the early universe was expanding much faster than predicted, a scenario that would require forces and particles beyond anything humanity has ever observed. Imagine the early cosmos as a vast construction site where the builders had access to tools and technologies no longer available today. Once those tools were lost, the universe continued its expansion under simpler, slower physics, leaving us to look back across time, trying to understand how it all happened so fast. These cosmic builders may have used techniques and forces that no longer exist, constructing massive galactic structures with tools that became obsolete as the universe evolved. Their ancient achievements now appear impossible when measured by today's physical laws. One idea, known as early dark energy, proposes a mysterious force that might have accelerated the universe's expansion during its first billion years. By stretching the cosmic timeline, it could have given galaxies extra time to form and merge. This early form of dark energy would have behaved very differently from the one driving the current expansion of the cosmos. Mark Kamienkowski of Johns Hopkins University suggests that unknown, exotic particles, unlike anything found in the Standard Model, may have dominated the physics of the early universe. These particles could have amplified gravity, altered how stars formed, or even provided new sources of energy for galactic growth. Another possibility involves the changing mass of the electron. If electrons were slightly heavier or lighter in the early universe, it would have reshaped atomic structure, chemical bonding, and stellar processes, potentially speeding up the formation of stars and galaxies while increasing their energy output. Some scientists also point to primordial magnetic fields, vast, powerful fields far stronger than those in the modern universe. These could have guided matter into organized patterns, boosted star formation efficiency, and sculpted the strikingly ordered structures the Webb telescope now observes. But these ideas don't just tweak existing physics, they rewrite it entirely. They suggest that the early universe might have operated under a completely different set of physical laws, which later transitioned into the ones we know today. Theories involving exotic matter propose substances with negative pressure or unusual gravitational behavior, capable of pulling matter together faster and more powerfully than normal gravity allows. Once their purpose was fulfilled, this strange matter could have vanished or gone dormant, leaving behind only the cosmic structures it helped create. Meanwhile, modified gravity theories propose that gravitational attraction itself worked differently in the early cosmos, perhaps stronger at vast distances or acting more rapidly than Einstein's general relativity predicts. These alternate versions of gravity would then have gradually shifted into the standard laws we now observe. Ultimately, the particle physics needed to explain Webb's discoveries pushes us far beyond the boundaries of the standard model, deep into the realm of bold theoretical speculation, where the laws of reality itself may have once been entirely different. The proposed new particles and forces remain purely theoretical. No experiment has ever confirmed their existence, and proving them would demand a complete revolution in our understanding of fundamental physics itself. Some scientists turn to string theory, extra dimensions, and quantum gravity for answers. Advanced frameworks that might have governed the universe only during its most extreme early moments. These ideas suggest that reality itself behaved differently during the universe's first billion years, shaped by laws that no longer apply today. If these new forces and particles truly existed, then one of two things must be true. Either our cosmic timeline is deeply flawed, or the early universe operated under physics so exotic, it barely resembles the cosmos we see now. This growing evidence hints that the expansion rate of the early universe might have been dramatically different, demanding yet another layer of hidden physics to explain how everything evolved so quickly. It's becoming clear the universe needs a new origin story, one that can explain the existence of massive early galaxies, impossible luminosities, and the rapid evolution revealed by the James Webb Telescope, all while preserving the observations that built modern cosmology. This new cosmic narrative could merge multiple theories. Perhaps the universe didn't begin with a single explosive Big Bang, but emerged from a pre-existing cosmic state, one that had infinite time to form structure before expanding into the cosmos we observe today. Hybrid cosmologies and blending, steady-state creation with Big Bang evolution, suggest that the universe may have passed through different eras, each ruled by different laws of physics. In one epoch, the rules allowed rapid structure formation. In another, they shifted toward the stable physics we know now. Other theories propose multidimensional evolution, where the early cosmos unfolded in higher dimensions that enabled galaxies to form at impossible rates. As dimensions collapsed into our familiar three, the universe locked in those ancient structures, preserving what should have been impossible. Some physicists even explore the idea of variable constants, that the speed of light, the strength of gravity, or even the mass of particles changed over time, opening brief cosmic windows where galaxies could grow faster than physics should allow. Quantum cosmology adds another twist. What if the universe didn't build its structure from scratch, but inherited it from deep quantum fields that already contained the blueprint of creation? This would allow instant organization, a cosmos born prearranged, not chaotic. Even consciousness itself has entered the discussion. If the universe operates more like a cosmic computation than a random explosion, then evolution might follow algorithmic rules. patterns that permit bursts of creation under perfect conditions. Meanwhile, dark sector physics proposes that most cosmic evolution happened through interactions we can't yet detect, hidden forces and particles, shaping the universe behind a dark curtain of invisibility. Whatever the truth, any new model must do more than sound elegant. It must make testable predictions, verifiable through the Webb telescope and the discoveries yet to come. Because rewriting our origin story isn't just science, it's philosophy. It's the question of what reality truly is. Webb's impossible findings have pushed humanity to the edge of understanding, where physics, time, and existence itself begin to blur. And as we stand at this cosmic crossroads, one thing becomes clear: the universe isn't broken. Our understanding is. The greatest story of all time, the real story of creation, is only just beginning.